If Samira she's joining us, I'll just add there.
Okay.
Okay, on this section 2, analyzing the recursive algorithms in chapter 3, we did an algorithm analysis where we check the technique for analyzing the efficiency of an algorithm. With a recursive algorithm, we will account for each operation that is performed based on the particular activation. Remember, activation record, it is where each recursive creates a space of a created name variable or namespace of that function that manages the flow of control at the time is executed. Stated another way, for each invocation of the function, we only account for the number of operations that are performed within the body of the activation. We can then account for the overall number of operations that are executed as part of the operation that takes place during the individual activation. As you analyze the non-recursive function that calls other function within the body. When we recall the computing the factorial in a relatively easy to analyze the efficiency of our function for computing the factorial, described in 4.1.1. A simple recursion trace for our factorial function was given in 4.1 to compute the factorial of n. We see that there are a total of n plus 1 activation as the parameter decreases from n in the first call to n minus 1 in the second call, and so on, until we reach the base, until we reach the endpoint of the parameter, which is 0. It is also clear, given examination of the function, that the body in the code of factorial function, that each individual activation of a factorial executes a constant number of operations. Therefore, we conclude that the overall of the number of operations for computing the factorial is a peak O of n, which is linear, and there are n plus 1 activations such of each account for constant time is peak of 1 operation. So we come back, Samira, drawing an English ruler analyzing the English ruler algorithm. A fundamental equation for how many total lines of outputs are generated by initial call to draw interval C, and where C denotes the center of length. And some intuition may be gained by examining the source code and recursion trace. We know that a call to trace interval of C for C is greater than 0 spawns 2 calls to draw the interval. For C is greater or equal to 0, a call drawn to interval C results in a precise C to the power of C minus 1, which means this the drawing a ruler is exponential. It's exponential runtime. We provide a formal proof of this claim by induction. Remember, we did in the last chapter, there was induction where we do by reasoning, how do we then find the algorithm? In fact, induction is a natural mathematical technique to proving the correctness and efficiency of a recursive process. In this case of the ruler, we note that the application of a draw interval at 0 generates no output, and that is 2 to the power of 0 minus 1. The 2 to the power of 0 is 1, so minus 1 is equal to 0. This is the case of our claim. More generally, the number of lines predicted by draw is 1 more than twice the number of generated by the draw interval is C minus 1. As C minus 1, we are similar as one sensor line is printed between the two lines, between the two such recursive calls. By induction, we then have that the number of lines is 1 plus 2 times 2 to the power of c minus 1, which is 2 to the power plus 1 to the power of c minus 2, which is equal to 3 to the power of c minus 1. This proof is indicative of a more mathematical rigorous tools known as recurrence equation that can be used to analyze the running time of a recursive algorithm. Performing the binary search, considering the running time of the binary search algorithm as presented in section 4.1.3, we observe that a constant number of primitive operations are executed at each recursive call of the method of a binary search. Hence, the running time is proportional to the number of recursive calls performed. The running times are, every time you perform a recursive, that's where we count our running time. So, and remember our activation record, wherever you're running a line, a call, it creates a space of that call. So we show that at most the binary search is log of n base 2 plus 1 recursive calls are made during the binary search of, so you can see, having n element leading to the following claim. The binary search algorithm runs in a peak O of log of n time for a sorted sequence with an n element. A justification to prove this claim, a crucial fact is that with each recursive call, the number of candidates interested to be researched is given by the value of I minus low plus 1. And then we run the mid, which is low plus n over 2 when it's low. If it's high, it's low plus 2 over 2 when it's high. So initially, the number of candidates is n after the first call. In a binary search, it is at most half or n divided by 2 after the second call. It is quarter, n divided by 4, and so on. In other words, recalling the weight omit logarithm base when it is a 2 or it is 2r is greater than log of n, thus r is equal to log of n plus 1, which implies that the binary search runs time the peak O of log of n time. Calculating the disk space code that we're running our final recursive algorithm section 4.1 was that of computing the overall disk space usage in a specific portion of a file system. To characterize the problem size for analysis, we let n denote the number of the file system entries in the portion of the file system that is considered. E.g., the file system portrayed in figure 4.6 is the n number of 19 entries. To characterize the cumulative or the total time spent for an initial call to the disk usage function, we must analyze the total number of recursive invocations that are made, as well as the number of operations that are executed within those invocations. We begin by showing that the precisely n recursive invocation of the machine, in particular one for each entry, is a relevant portion of the file system. Intuitively, this is because of a call to disk usage for a particular entry E of the file system is only made from within the for loop of the code segment 4.6 when processed. To formalize this argument, we then define the nested level of each entry such that the entry as which we begin has nesting level 0, entry stored directly within it. And then having established that there is a one recursive call for each entry of the file system, we return the equation of the overall computation time for algorithm. It would be great if we could argue that the spend time is constant time or the peak of 1 in any single invocation of the function, but this is not the case. while the constant number of steps reflected in the call of the OS part to get size to complete the disk usage directly at that entry when the entry is a directory. The port of the disk function include a follow that indicates on the entry level containing with the directory. In that worst case, it's possible that one entry includes n-1 others. Based on this reason, then we could conclude that they are a linear time peak of n recursive calls. Each of these runs on linear times again. So we need to times n times n, which leads into the overall running time that the running time of this program is peak of n squared, quadratic. While the upper bound is technical true, it is not a tight upper bound. Remarkably, we can prove that the stronger bound that is recursive of the algorithm completes at a linear time. The weaker bound was pessimistic because it assumed the worst case number of entries for each directory. For each directory, due to the loop of a linear, summing all the overall of operation is linear. The argument we have made more advanced than the earlier example of recursion. The idea that sometimes gets a tighter bound on a series of the operation by considering the cumulative effects rather than assuming that each achieves at worst case is technical code amortization, which will be explained in later in the next chapter. Further, the file system implicitly example of what is a structure called a tree. Our disk usage algorithm is usually a manifestation of the more general algorithm known as a tree traversal. Trees will be on the focus of chapter 8. To just highlight a little bit of the tree is this from here, and each time give birth to two branches. It continues like that. So each chart give birth to this. This is what they call the tree, but it is upside down tree. So this is what they called the tree traverse. Okay, also we did see on that disk on that algorithm, this calculating was calculate the files. Section 3, recursion run amok. Although recursion is a very powerful tool, it can easily be misused in various ways. In this chapter, we check where we can have a problem when running the recursive. We begin by revisiting the element uniqueness problem defined in the section 3.3, where we can use the following recursive formulation to determine if all elements of the sequence are unique. As a base case where n is 1, when n is assigned to 1, the element are trivial unique. For n is greater or equal to 2, the element are unique if and only if first element of n minus 1 element are unique. And then the last n minus 1 items are unique, and the first and last element are different. That is the only pair that was not already checked on such case. A recursive implementation based on this idea is given in 6.4, the unit 3. The function run like this to define the function. It has a parameter s, which is the list where to start or where we end. If the stop run is done M2, if not unique, return false. If not unique, return false until the last one went to the first and last. Unfortunately, this is terrible inefficient use of recursion. The non-recursive part of each call uses the constant time. It runs on constant. So the overall running time will be proportional to the total number of recursive invocation. To analyze the problem, we let n denote the number of entries under consideration. In essence, that is n is equal to stop minus start. If n is 1, then the running time of the unit is constant, since there is no recursive call for this case. In general case, the importance of observation is that a single call to unique for problem of size n may result in 2 recursive calls on a problem of size n minus 1. Those calls with the size n minus 1 could in turn result in 4 calls each, with the range of size n minus 2 plus 8 calls with size n minus 3 and so on. That the worst case total number of function calls are given by the geometric summation, which is equal to n2 to the power of n minus 1, the proportion of 3.5. This running time of function unique is big O of n to the power of big O of 2 to the power of n, which is exponential. This encrypted inefficiency, it is become too slow, and it doesn't help us as we compute it. An efficient recursive for computing the Fibonacci can use also the same way to do the paid Fibonacci. If n is less than or equal to 2, return n. If n is less than, and then or else return the Fibonacci. Unfortunately, such direct implementation of the Fibonacci formula results in a terribly inefficient function. Computing the n Fibonacci number is this way, resulting in another exponential above equal to function. Still doing the Fibonacci. The better one, in this time we're running Fn, but you offered with more variable or more argument, and then we manage it one. So it decreased by one aspect. In the terms of efficiency, the difference between the bed recursion and the code for this problem is like the day and night. Bed function uses exponential time, while the code recursion takes linear time. Each recursive call to code decreases the argument by 1. Therefore, the recursion traces include a series of n function calls because of a non-recursive work for each call using a constant time. The maximum recursive depth in Python. Another danger in misuse of recursion is known as infinite recursion. If each number recursive call another recursive call without ever reaching the base, if our loop, if our recursion goes infinite, it keep on going back. It keep on going back. It end up crashing the system. So this is what we call infinite recursion. It is the bad recursion if it doesn't have a base. If there's no base, then it's gonna go until it crashes your CPU. Python typically has a 1000 default value where you can end your system so that you're not gonna crash your system. You say if you reach beyond 1000, and then it says ransom error, give you a message, maximum recursion depth exceeded. You can upgrade it, but also it depends on how big is your system, how big is your computer. A further example of recursion, we got linear, we got a binary recursion, and then we got a multiple recursion. If a recursive call starts at most one other, this is where you call a recursion. If this is where you call a linear. If it calls two, like the name says binary, it means you call it a binary recursion because it's called two. from the binary by digit. And then if the recursive call may start 3 or more, we call this the multiple recursion. If the recursive function is designed to so that each invocation of the body makes at least one new recursive call, this is known as a linear recursion. Of this recursion, we have seen so far the implementation of factorial function, which calls each time one invocation. Ironically, the binary search that we're using, it's also called a linear, despite using the binary name, including a case analysis, 2 branches that lead to a recursive call, but only one of those calls can be reached during the particular execution of the body. And then a reverse, okay, we're still on a linear regression. And also when we're doing the powers computing, you do the same thing, turn on the linear, goes there and then comes there. Binary recursion, when a function makes 2 recursive calls, we say that it uses a binary recursion. We've already seen example, several examples of a binary recursion, most notable when you're drawing an English ruler. English ruler means it's using a binary recursion. And also in the bed Fibonacci function, where our implementing we use or more element, we can recursively compute the sum of the first half. This is a binary recursion where we're looking for more first half. To analyze the algorithm binary sum, we consider for simplicity the case where n is the power of 2. I show that the recursion trace of the execution of the binary from 0 to 8, we label each box with a value of parameters that from that, which we're using the slice algorithm. From here, we're using the panel. It's like a tree, a triangle. This give birth to this give birth to this, and this. And that's why we call it a binary recursion. A multiple general of the defined multiple recursion is a process in function, which a function may take more than 2 recursive calls. Our regression for analyzing the text space usage of the file system in the previous section. In an example of a multiple recursion, because of the number of recursive calls made during one invocation was equal to the number of entries within a given directory of the file. Another common application of the multiple recursion is when we want to enumerate various configurations in order to solve a combinatorial puzzle. For example, the following are all instances of what we know as summation puzzle. To solve a puzzle, we need unique digits as from 1 to 9 to each letter. The equation, in order to make an equation true, typically we solve such a puzzle by using our human observation. Particularly the puzzle we're trying to solve to eliminate the configuration that is possible partially assignment for digit 2 letters until we can work out possible configuration from left and set for the correctness of each one. The algorithm here we run put solving the puzzle we put. If we have input, we run the output, we do a for loop, and then we check if this is 1, and if it's not, and then we run the for loop. And this one gives us the multiple of regression where it gives us not only just 2, but more than 2. We check for this argument for 2A and BC, 2B, AC, and etc. The key trace for an execution of the puzzle solve 3S and U, where S is the empty set and U is the APC. This execution generates and tests all the permutation of A, B, and C. And section 5, designing a recursive algorithm. Designing a recursive algorithm must always a good one. Must always have a test. Must always have a test to check your base, and then it can recall. We begin by testing the 4 sets of the base cases, which there should be at least one. Otherwise, if it doesn't have, then it's going to call infinite, which is a bad algorithm. And then if not this, then it should perform one or more recursive calls. The recursive step may involve a test that decides which of the several possible recursive calls to make. Parameterizing the recursion to design a recursive algorithm for a given program is useful. It's useful to think of the different ways we might define our subprograms that have the same general structure as the original program. If one has a difficulty finding the recursive structure needed to design a recursive algorithm, it is sometimes useful to work out our problem on the few concrete examples seen in a subprogram defined. A successful recursive design sometimes requires that you've redefined the original problem to facilitate similar looking subprograms. Often this involves reparameterizing the signature of the function. For example, when performing a binary search in a sequence, a natural function's signature for a caller will appear as binary search. Remember the first one we were using for parameters, but here we have 2. However, in section 4.1.3, we use our function we call it we use data, target, low, and high. So using the additional parameter to demarcate the sublist of as the recursion proceeds. These changes in parameterization is critical for binary search. If we had existed on the cleaner signature binary search of the data and target, the only way to invoke a search on the half the list will have been to make a new list instance with only those elements sent as the first parameter. However, making a copy of the half list will already run a linear time, the peak of n, negating the whole benefits of the binary search. If we could wish to provide a cleaner public interface to an algorithm like the binary search without bothering the user with the extra parameters. The standard technique is to make one function for public cleaner interface such as the binary target, and then having the code invoking the non-public utility. Using the inheritance system. The simplified one, the cleaner one, will be public, and then the public will call and the one that has the 4 parameters, which is non-public. Eliminating the tail recursion, the main benefits of recursive approach to algorithm design is that it allows us to statistically take advantage of a repetitive structure present in many programs. By making our algorithm descriptive, exploit the repetitive structure in a recursive way. This often avoid complex cases analysis and nested loops. This approach can lead to a more readable algorithm description while still being quite efficient. So for even better forms of recursive can be eliminated without any use of auxiliary memory. A notable such form is known as tail recursive. A tail recursive is a recursion if any recursive call that is made from one content to the very last operation in that context, with the return value of the recursive call, if any, immediately return by enclosing the recursion. By necessity, a tail recursion must be a linear recursion. So there's no way to make a second recursive call if you must immediately return. Our recursive function demonstrated in its chapter binary search of the code 4.3 and the reverse function of the code 4.10 example of detailed recursion. Several others of the linear regression are almost like detail, almost like detailed regression, but not technically so. For example, a factorial function of code 4.1 is not a tail. It includes the command. It includes the command of multiplying the factorial at the last command. This is not a tail because an additional multiplication is performed after the recursive call is completed. The binary search, which is much more simpler, this one binary search of data called data and target. It ran lower and then it declare lower to 0, and then high. It define the length of the data with the -1. So if the data say are 10, so it's from 0, and then from the length of data 10 minus, which is 9. Why the lower is less than or equal to high, then we declare the mid, which is mid is lower plus high divided by 2. If the target is found, you return true, or else target is less than mid, which is high, less than to mid minus 1, or else lower, high you add to 1, then return false. The target or the narrow of the range of the candidate subsequence where we made a recursive call binary search where we have 4 parameters in the original version. Simply replace the high with a mid minus 1 on our version, and then we continue to the next iteration. Okay, we have exercise. Okay, with this 3 minutes, let's see we can do this exercise. Describe a recursive algorithm for finding the maximum element in a sequence S of n element. What is your running time and space? Define the function. Describe the recursive. Define the function recursive of the maximum element in a sequence. So let's say rook find max by giving this is a list S of index. If index is equal to length of S, and then -1, we return max. It is an index, and then return max as max index, and then run again the function index Then you need to define the function file max. What is a step recursive algorithm for finding the maximum element and run the max at 0. Let's see one argument return rec is at 0 and then just print it.